All right, let's start. Do you have any questions? Okay, so we were discussing 6.1. Joint distribution functions. And so the point here is, right, that last time we discussed to put two random variables, but here we can, make it a little bit more general. Suppose you have x1, x2, and then xn, right? These are random variables. Then we can look at the joint CDF of x1 to xn as f, right? You can do this to kind of signify, right, that you're looking at the joint, then the joint CDF of these random variables, which is the probability that right, these random variables are below these values or equal to. And so basically, right, that's right there is what we mean by joint behavior. And I think, right, at the heart of it is just really this intersection, right, of events. Meaning what? X1 less equal to x1, x2 less equal to x2, xn less equal to xn, right? That's it. So the point is, from the previous chapters, we know what these are, right? From the point of view of random variables. And so they're random events, right? But they're random events associated with an object, right, being in a range of values. And so when you look at the joint distribution, you just kind of take that concept and generalize it to the n dimension, right? So instead of having a one-dimensional sort of range of values, now you have n-dimensional, right, range of values. So it's on Rn, for example, and you look at, right, the probability that the random event, right, that your random vector, if you will, is in certain range of values. And in a CDF case, it's less than equal to like kind of some points, right? And so, for example, I mean, it can be done with n points of values, but the most popular case, of course, is when n equals to 2, because we can draw a picture here, right? So when n equals to 2, then the picture, right, is that basically we can visualize this as, so here's x1, right, here's x2. If at the point x1, x2, then you're looking at sort of the area, right, to the left of x1 and below x2, right? Like that. Of course, this is not exactly the area of the rectangle as we think of it as like, um, the Cartesian area, right? It also depends on how you assign the weights along, but the area like that we're looking over, right, is exactly these ones. And so because of this kind of picture, right? And then, to demonstrate it's just really working, it's just really like probabilities, then we have this probability, right? A1 less than x less than equal to A2, and then y B1 less than y less than equal to B2 is f, so fxy, right? A2 B2 minus f A1 B2 minus f A2 A2 B1 plus f A1 B1. And so again, it's really just the inclusion exclusion formula here, right, for the events. So if you look at, right, so this instead of A1 B1, so how to say this, right? Here we kind of switch the rotation and say this is x and y, right? Then you have A2 B2, right? And then you have A1 B1, let's say, right, to the left of that. So it doesn't matter, right? Well, it is, right, to the left and below that, right? So the probability that let's say you're in this range, right? The area of this range is, of course, right, the rectangle, right? This rectangle, subtract, right, this rectangle, and then subtract this rectangle, right? Sorry, this rectangle, right? Well, you see that, hold on. No, I'm saying something nonsense, right? Sorry. So the area over here, right? That's what I'm saying. That's what I should say, right? That's the area between A1, A2 and B1, B2, right? This area is the big area, right, of the rectangle, subtracting, right? So this big area, so first of all, subtracting this rectangle, and then subtracting this rectangle. And then you see that this part is being subtracted twice. So you add back once, right? Which is the fxy A1 B1, right? The area to the left of this rectangle. So anyway, right, it's just really the inclusion exclusion formula at work. Again, showing, right, that this is nothing but just the intersectional events, as how we look at it. Now, when we have discrete random variables, if x, y are both discrete, then we have the joint probability mass function. So we can just not just xy, x1 up to xn, right? Because you can have more than one random variable for the joint distribution. Then we have probability of x1 equals to little x1, x2 equals to little x2, xn equals to little xn, right? Like that. And again, this is just the intersection, right, of events. So, right, it's nothing more than probability of x1 equals to x1 and x2 equals to x2 and etc. And, right? So if we know how to handle intersectional events, then we can handle this thing. That's all there is, right? So, of course, just like random variables in general, that they take random events, right, and associate them with numerical values. So here, with joint distribution, we also take random events, but we associate them with numerical vectors, right? Because we know we go with higher dimension. And then when we associate them with vector, then we look at then this that sense of intersectional events that we're looking at. Okay. And so if it's intersectional of events, then the law of probability works just like how it works. For example, if you look at the case when you only have two random variables x and y, and if you sum over all values of possible values of y, for example, then this being intersectional events, if you sum over all possible values of y, then this is the law of total probabilities, right? And which gives you probability of x equals to x. Similarly, right, if you sum over all possible value of x, this is the law of total probabilities. This is probability y equals to y, right? So this is called, right, of course, the marginal distribution. Okay. And basically what it means is you can integrate out or sum out, right, the other random variables to get the marginal distribution of the random variable you're interested in. But again, here we call it that. We give it the name of marginal distribution. But at the heart of it, right, it's just really the law of total probability, right? So in the case of n random variables, it's the same thing, right? It is sum over all possible values of the remaining variables. Right, and what I mean by that is you sum over all possible values x2 up to xn, then you get the probability of x1 equals to 1. X1 equals to x1. Now, so for example, to be concrete, right? In your question number 6.2, right? You say that they are supposed to have 3 balls chosen without replacement. From an urn consisting of 5 whites and 8 reds. Let xi be 1 if the ith ball selected is white. Right? So see, for example, potentially, right, your x1, x2, x3 as a vector, right? and as a joint distribution, we'll take values, right, on, so each of these, right, can be 0 or 1, right? So together, right, they take the possible values. Eight possible values, right? From 0, 0, 0, 0, 1, 0, etc., right? Up to 1, 1, 1, right? Sorry, and 0 otherwise, right? Should say that. So to demonstrate what we're saying here, right? What I mean is, for example, that probability, let's say x1 equals to 0, will be equals to the sum of probability x1 equal to 0, x2 equals to I, x3 equals to j, where ij equals to 0 or 1. Does that make sense? Right? If you sum over all possible values that x2 and x3 can take, namely zeros or ones, you get back the marginal of x1 equals to 0. Now, if we want to write down, right, the joint distribution of x1, x2, x3 here, for example, then all you have to do is to think of, right, what it takes for, let's say, these events to happen. So it's really, right, a description of probability of the first ball selected is white, second ball selected is white, third ball selected is white, etc. So the statement, right, of the random event is this and that and that. It may or may not be easy to calculate the probability of such an event, but abstractly, right, that's all we mean, right? For example, right, so the joint, right, mass probability distribution function, right? So for example, 0, 0, 0, right, will be what? So 0, 0, 0 means all three balls selected without replacement has to be red, right? So something like 8 over 13 times 7 over 12 times 6 over 11, right? 0, 0, 1, for example, right, will be, so the first two selected are reds, but the last one will be white, right? But notice that when you see that, this number, right? Again, this has nothing to do with like joint distribution, but if you look specifically into this question, then it doesn't matter, right, where the one is. The answer always come out as the combination of 8, 7, and 5. So you can say that this is right. They're all. So basically, the joint mass probability function for these three values are all equal to this, right? Similarly, the joint mass value for 1, 1, 0, the mass probability function, right? For 1, 1, 0, 0, 1, 1, 1, and 1, 0, 1, right? They're all what? So you need two whites, right? So 5 over 13, 4 over 12, and then 1 red, right? Like that. Of course, when we do this, we're thinking of this particular case. But when you look at these two other ones, right, they both come out to be the same number. And finally, right, 111 will be all whites, right? 5 times 4 times 3 over 13 times 12 times 11. Okay. So again, we're just writing down a particular example, right, for this particular problem. And there are different variations that you have to work out, right, in your homework. But at the heart of it, it's just really reading the description of what the experiment is about, and then write down, right, the joint event of whatever that's happening. Whether it's kind of difficult or easy depends on the question itself. But, you know, the language of it, right, the joint mass function really is just about this and that and that. That's all I want to say. Okay. Any question about this? All right. So now, so that's discrete random variable, right? So for x and y, continuous random variable, if x and y, you know what? Let's again do this more generally. If you have x1, x2, xn, they're all continuous random variables. Then what we will have is something called the joint PDF. Okay. Function of these guys, which is f, x1, x2, etc., xn, evaluated little x1, x2, xn. Okay. So what properties does the joint PDF have to satisfy? The first thing is that it must be non-negative. The second thing is the multiple integrals, right, of the joint PDF. So over support, right, must be equals to 1. So just like the regular PDF, where it has to be non-negative and it integrates over the real line, right, to be 1. Here, the joint PDF has to be non-negative and it integrates over the Rn, right, region would be 1. But in reality, of course, you just integrate over whichever, like, you know, the relevant support will be. And the probability, right, that let's say x1 less than equal to little x1. So the TDF, right, the joint CDF is the integral, right, is the multiple integral of the joint CDF, of the joint PDF. The joint CDF is the multiple integral of the joint PDF. So now the subscript, you could skip it, sorry, and also I forgot here, right? This is dx1, dx2, dxn. Right. Okay. Let me change this to A1, A2, etc. Because I use x as the integrating random variable. integrating variables. So minus infinity to a1. So notice you have to kind of match up, right? X1 is the inner integration. So I integrate X1 first from minus infinity to a1. And then I integrate X2 will be minus infinity to a2, right, etc. So the two outer one would be minus infinity to an minus 1, and this is minus infinity to an, right, the last one. Now, of course, by Fubini's theorem, you can swap the order of integrations here, right? But you have to also change, right, the limits of the integration appropriately. And this is where, right, your Calc 3, let's say education, right, comes into play. Of course, you can also write down the probability that a1 less than equal to x1 less than equal to a2, right? Sorry, a1 less than equal to x1 less than equal to b1, a2 less than equal to x2 less than equal to b2. Then the limits here will go from a1 to b1, a2 to b2, an to bn, right? Rather than minus infinity, a1, etc. But so the joint PDF, right, and the joint CDF are straightforward, let's say, generalization, right, of the PDF and the CDF of a continuous random variable. It's really just kind of taking that concept, right, and generalize it to multi-dimension. Yeah. Okay. So maybe also, right? So the joint CDF is the multiple integral of this. The joint PDF is the partial derivatives, right? Of the joint CDF. And let's just write down, right, the case when there's two random variables. So if you have the joint PDF of x and y, that's the partial with respect to A and B of the joint CDF, for example. Y, well, is really just from that formula, right? So in general, you would differentiate the joint CDF with A1, A2, AN-1, AN, right, respectively, to get to the joint PDF. Okay. So let's look at an example. And this is called the uniform distribution over a circle. So the idea is pretty simple. Suppose we have a circle, right? I think I should draw it a little better. So we have a circle, right? Center at 0 with radius r. And we look at, right, a point randomly chosen and I think we discussed this before, right? A point randomly chosen inside, right? Or let's just say in, yeah, a circle, right? Centered at the origin and radius r. So we discussed that here randomly chosen can have different meanings. So here, when we say this in the sense of the joint distribution, the default sense randomly chosen here is area-wise. Well, what do I mean by that? What I mean by that is that basically the density, okay, over the region where you say it's uniform is constant. And what region are we looking at? Of course, we say we chose it randomly inside the circle. So what we mean is the support, right, is the circle. Now, just like, right, maybe I should mention one thing. Just like the one-dimensional case where the probability, right, that is equal to a single value is equal to 0 if x is continuous. The same thing happens, right, for multidimensional distribution or joint distribution. In other words, probability x1 equals to 0 x1, x2 equals to 0 x2, xn equals to 0 xn will be equal to 0, right? So the probability that it takes on equal to a particular value will be 0, right? And you can see or generalize this to the probability that it's going to be exactly on the edge of the circle is 0, or on the boundary of a circle is 0, right? So basically anything that has lower dimension than 2 dimension, it has probability 0. But anyway, the support, right, is either inside the circle or inside the circle, including the boundary. It's the same thing, right? So what we're saying then is the joint PDF will be a constant if xy is such that x squared plus y squared is less than or equal to r, and then 0 otherwise. So sorry, r squared. Okay. So that's what we mean by a uniform distribution over a circle. The density over the region is constant, not in any other sense, right? You could, in principle, choose this uniformly in terms of the circumference over a circle. But yeah, in that sense, it's still kind of, it can be interpreted as randomly chosen in the circle, but that's not the default sense that we mean, right? When we say uniform here, we mean the density over the region is a constant in this way. So it's uniformly chosen area-wise or volume-wise, whatever, right? If it's three-dimensional or higher. All right. Any question about the description here for this random variable, this joint distribution? Okay. So let's see if we can work this out. For example, right? Quiz 1. What is C? What is C here? Well, what must happen? What must happen is that, right, the double integral right, over the circle of the joint density must be 1, right? But what is the joint density? Is a constant. So the constant can be factored out, right? And what is this? From Calc 3, right? This is the area of the circle. Notice, right? Calc 3 comes in a lot here. And in fact, right, chapter 6, especially when we talk about the joint density, it's all calculus 3 knowledge in terms of like the actual, right, carry out of the calculation, etc. So C is 1 over pi r squared. Okay, so far. Second question. Find the probability that the distance from the origin of the point selected is less than some value A. And for what kind of value, for what kind of what kind of A is appropriate here? A clearly is between 0 and R. Right? What's the answer? So first of all, right, if you approach this from the joint density point of view, what are we looking at? We're looking at, right, so the probability of whatever we're looking at, distance less than A, will be the double integral of the joint density over that region. Right? But, well, for other distributions, it might be different. But for the uniform distribution, right, since this is constant density, the density will factor out. And so for uniform distribution, you are very often talking about the area, right? Because when you integrate this, this is the area. Area of what? Area of the region inside the circle whose distance from the origin is less than A. which is what? Pi a square, right? And C is 1 over pi r square. So the final answer is a square of r square. Any question with that? Okay. So what can we do with the joint density? Well, besides, right, calculating probabilities and things like that. Well, we can do the marginal density, right? So marginal densities. Well, what would this be? Just like marginal distribution function. So suppose you have the joint PDF like this, and you want the PDF of, let's say, x sub k, right? What can you do? Well, you can integrate out everything else. So let's say you integrate out dx1 and then xk minus 1 and then xk plus 1 and then up to xn, right? So this is just a complex way to say that you integrate out everything but xk. You will get the marginal PDF. Sorry, yeah, marginal PDF of xk. So if you have only two random variables, then if you integrate out the y part, you get the PDF of the x. And if you integrate out the x part, then you get the PDF of the y. Right? Just exactly like the law of total probability, but now it's a density version. Any question? So here, maybe let's write down a few line of proof, right, for why this is true. Because with the continuous random variables, right, I said the main point is to distinguish between PDF and CDF, all right? You don't operate on PDF directly when it comes to probability. You operate on CDF, and then you differentiate CDF to get to the PDF. So to find the, let's say, marginal density, let's work with the case when you have two random variables, right? You want to start with the CDF, right? And if you differentiate this, you get the density. But what is the CDF? What in the joint sense? Because you have the joint density, but this is one random variable, right? Doesn't matter because you can always throw in a y like this. Right? And then you can write this down as so this is a X has already been used, right, for this. So I have to use a dummy UV. Okay. And now I will need to differentiate, right, to get to the PDF. So if I differentiate with respect to X, right, that means I have to differentiate with respect to X of this multiple integrals. But here, there are two ways you can think about it. The first way is I can pass the the differentiation operator inside the first integral and just hit it with the second integral, because that's where X is, right? Or I can do a Fubini change of integration order, and I can switch this to dv du and bring the X outside so I can differentiate with respect to X. The end result is the same thing, meaning that I just have to differentiate with respect to this integral and ignore the other one, which I will get, right? And if I differentiate this with respect to X, then I have a fundamental theorem of calculus going on, right? Where I will replace this with the X letter. The V is still the same, right? This is differential with respect to X, and this is du. So I just replace u with X, meaning that I have f x y x v dv. And that you can verify, right, is exactly that. But instead of using y as the integrating variable, I use v. It's the same thing. Do we understand? Any question? So now, right, let's apply this to this example. And let's ask you to find the marginal densities of X and Y here. Right, so let's reconsider the circles of radius r, right? Find the marginal densities of X and Y. So what's the answer? So let's say you want to find the marginal density of X. And so the the theories, right, basically says that you just integrate out the Y, right? Integrate out the Y. So it will be 1/pi r squared, right? dy. But again, right, in the abstract, in the absence of any further information, we just say we integrate out over all range of Y's. But in practice, right, this will be some concrete range of values. What are they? With respect to this circle, where do we integrate Y from? From where to where?
Negative r to r.
Incorrect. Because, right, minus r to r will go from here to here. Sorry, integrate Y, right? Go from here to here. But when you do that, you are not taking into account that this is a joint distribution. This is a PDF of X at this particular value of little x. Okay, let's make that clear. Let's say, suppose little x is over here. Then does Y go from minus R to R? No, right? Y here, the range of Y's depends on the X. And that makes perfect sense, right? Because where X is will determine where Y can, what values Y can take. You understand? So in this way, it might be a bit subtle, but X and Y here are not independent. Where X is will determines well what kind of values Y can take and vice versa. If it's literally minus R to R, then very probable that they're independent. But here it's not. It's going to be from minus square root of R squared minus X squared to square root of R squared minus X squared. Do we understand? It's from here to here. So the answer is 2 square root of R squared minus X squared over pi R squared. For what range of values of X? From minus R to R. Any question? What about Y? You should expect that the answer for Y is the same, right? Replacing this with Y because it's symmetric. And that's true, right? But again, right, the picture here is for a fixed value of Y. Then X, right, can only go from here to here. That's the only possible values of X. Do we understand? Any question? All right. So now let's talk about expectations. Of joint distribution. And I will talk about the discrete and continuous case. And I will talk about a function of joint distribution. So what I mean is this, right? And let me just you know what? Let me write down the n-dimensional case and I'll write down the two-dimensional case. So for the discrete case, it'll be like this. For any function of x1 up to xn, it will be the sum over all possible values of this function times the probability that x1 equals to x1, x2 equals to x2, xn equals to, sorry, big Xn, like that. So, for example, right, remember that one where we look at, right, x1, x2, x3 takes on possible values 0, 0, 0, 0, 1, 0, etc., right, up to 1, 1, 1, right, 8 values, right, 8 possibilities, let me just say. Right. Then you can have something like expectation of x1 times x2 times x3 as the sum, right, over the product of these numbers times the probability that x equals to these numbers. But you can see, right, so let me just write that down. But you can see that because we're looking at a product, the only thing that will survive the product here will be 1, 1, 1. So it's literally, it's just probability x1 equals to 1, x2 equals to 1, x3 equals to 1. I mean, for this particular example, of course, right, not all will be like that. But for the example we just talked about earlier today, the sum here, right, will boil down to just one single number, like that. And if you want to look at, let's say, another function like the sum, then it will be the sum I guess we should say belong to, right? x1 plus x2 plus x3 of like that, right? And then you can do some analysis. But for example, right? So 0, 0, 0 doesn't contribute. 0, 1, 0, right, will give you 1, right? So that will be 1 times, right? Rather 3 times. Why? Because we argue that these guys are equal, right? Whether it's 1, 0, 0, 0, 1, 0, or 0, 0, 1. And then you have 3 times 2 times why? Again, because we argue that these guys are equal, whether it's 1, 1, 0, 1, 0, 1, 0, 1, 1, right? And then finally, we got 3 times. And whatever they are, right? Whatever the numbers we wrote down before. That's what that is. Do we understand? Any question? All right. So that's the discrete, right? For a continuous case, it's the same. But it will be the integral against the density. Against the joint density. Like that. So for example, right, again, let's take a look at the uniform over the circle, right? We let D be the distance of the point, right? So basically, of course, this is the density of a point selected, right, randomly or uniformly over the circle. So the distance of the point from the origin, right? So this is quiz 4, right? Find expectation of D. So what is it? So here's a little bit difficult, whatever, right? In the sense that the function is not named explicitly, but it's implicit, right? Because what is D? D will be square root of x squared plus y squared. Agree? Notice it's a capital X and Y because we're looking at the random point. All right, the point is X and Y. Okay, so D is a random variable, right? And notice also, in a sense, you are making a one-dimensional random variable out of a two-dimensional random variables or a joint distribution. So you're combining the joint distribution or two-dimensional random variable into a one-dimensional random variable, right? Of course, there are many ways to do that. This is one way. And so expectation of D then is just the integral over the circle, because that's the support, that's everything, of integral of x squared plus y squared, 1 over pi r squared dx dy. So what's this? What is this integral? Well, this is where your Calc 3 again is required. Well, to do this, you need to do polar coordinates, right? So this will be the integral of square root of r squared r d theta. Factor this out, where r goes from 0 to big R and theta goes from 0 to 2r. So we need to switch to polar to do this integral, right? And let's see here, right? That's r, because r is positive, that's r squared. So that's r cubed over 3 times 2 pi, right? And then times pi r squared. So the final answer is 2/3 r. Notice, right? The unit makes sense. The unit is correct. It's a unit length. And it says that on average, right, you will be 2/3 along the circle. Which also seems to make sense because if you pick the area uniformly, right, you pick it uniformly over the area. So you think of it like, it's like you're throwing dart, right, to the circle, uniformly along a circle. Then because sort of like it's uniform over the area, you tend to kind of like, be over the bigger area more, right? Because there's more area there. So you tend to be more out than in, right? So you're 2/3 way out. Any question? So let me tell you here as well, right, on this topic of expectation. Then probably the most common expectation you will take is the notation of covariance, right? Which is the notion of for two random variables. So covariance of x and y, first of all, will be expectation of the product. Right. And first of all, right, notice how it's like the interaction between x and y, right? Because it's the difference, right, between x and, so you kind of centralize x, right? You subtract away the mean, right? So this is mu x here, right? The average of x, this is mu y. And you look at the product. So you look at the interaction of x and y somehow. And on the other hand, if you look at, if you distribute this in, right, this is xy minus x expectation of x minus y expectation of y plus, right? And then you use linearity of expectation. You get expectation of x times y minus, right? This is sorry, I'm wrong here, right? This is xey and then yex. So you got exey, exey. So you get expectation of the product minus the product of expectation. And that's sort of like the computational, right, formula for covariance. But this is like the understanding, right, the definition, the conceptual definition, and this is the computational definition, right? And they're equivalent. So let's see. How do we apply this? And I'm trying to think. I'm trying to see if with this circle it's easy or hard. Because you see, if I'm not careful, some of the question, the integration may not be that nice. So let's maybe reserve this for some other time, right? But this is, in principle, this can be done for any distribution because this is just expectation of a function or random variable. But you know what? Let me say this. So with respect to this, right? With respect to the previous uniform of the circle, write down the multiple integrals calculation for the covariance of xy, but do not calculate. All right. So the reason is, I don't know if the antiderivative is going to be easy or hard. So let's not even get into that for now. But I want you to write down the multiple integrals with respect to this distribution, right? For the covariance of x and y. At least so you see what the calculation should be. Okay. So what should it be? So you have expectation, right, of x times y minus expectation of x, expectation of y, right? So expectation of x times y is little x times little y times the density, which is 1 over pi r squared dx dy, right? Now, if you integrate over the circle, then what are your limits? Well, so you do dx first and dy later, right? So the x must go from, for fixed y, minus r squared minus y squared, square root, to square root of r squared minus y squared, where y runs from minus r to r. Now, of course, if you anticipate that you will convert this to polar right away, you could write down x and y in terms of polar and rewrite this in terms of polar. It's up to you. But if you do rectangular coordinate, this is the expectation of x times y. What of expectation of x? Well, expectation of x in terms of the joint density is still the same because x can be viewed as a function of x and y. So it's just x times that. And you integrate x first, right? So this is expectation of x. And of course, expectation of y is the same, but I'm gonna label the point and write down the integral for that. But you see in reality, right, these are the same numbers because they're the same integral. So you can just take this and square it. But I'm just writing it down so you can kind of clearly see it. X, expectation of y in this case.
You're still integrating with respect to x first. Do you need to have r squared minus x squared?
I appreciate it. This should be dy dx. Thank you. That's the mistake I made. Yeah, thanks. It's dy dx because I'm integrating y first for fixed y and then x out. But I could also do this dx dy with, yeah, either way. Any other question? Okay. So maybe let's do one more question. And this is from question 6.8. So they say that they give you a joint density, which is like this. Okay. So the joint PDF. A, find C. So what should be? So it's a good practice, right? Especially with multiple integrals, to have some rough idea of what the region looks like. So the region, right, is y is positive, right? And x between minus y and y. So it's this V-shaped region right here, right? That's what we're dealing with. That's the support. Right, this is the support of the pair of the random variables. So whatever C is, notice also, right, over this region, this guy is non-negative as long as C is non-negative, right? Because y squared minus x squared will be positive actually, right? So this will be the double integral of y squared minus x squared e to minus y d. And here let's ask, do we want to do dx dy or dy dx? This is a classical Cal 3 question, right? Does it matter? Or should we do one rather than the other? I mean, sometimes it doesn't matter, it doesn't help, but at least we should think about that. Dx dy, dy dx, does it matter? And of course, right, the equality here should be 1, right? And then c times that. But should we set the integral of dx dy or dy dx? Answer, I think dx dy might be better here. Why? Because if you dy first, then you're gonna end up dealing with a integration by parts, which is, not that bad, but let's say that let's try to see if we can avoid it if we can, right? So if you do dx dy, then first we integrate respect to x, so we may be able to avoid, right, the double integral. Who knows? But let's see what it takes. If you dx dy, then it also says, right, it's also kind of nice because x goes from minus y to y and y goes from 0 to 0. Right? And so what is it? So x, right? So anything with respect to x can factor out. So you got, right? So the first integral you see is y squared e to minus y times 2y. Right? So the first integral is 2y cubed e to minus y. Subtracting, right? The second one is x cubed over 3, right? X cubed over 3. And then x cubed over 3, plug in y minus y. I can see here it doesn't help, but 2/3. Agree? Any question? And so, right, this is what 2 minus 2/3 is 4/3, right? And so we have to integrate this. But the good news is we only have to do it once, right? Let's see the reason why. So that's 4/3 c, right? 3y, sorry, we integrate this and differentiate this, right? So y cubed minus e to minus y, 30 plus integral of 3y squared e to minus y. dy. Right. This is 0, so we can ignore it. This, we don't have to do further integration. We know the answer is 2. Well, how? This is the second moment, right, of the exponential with parameter 1, which is the variance of the exponential 1, right? So this is expectation of x squared, where x is exponential 1, which is the variance of x plus expectation square of x. But the variance of an exponential lambda is 1 over lambda, so that's 1 plus 1 equals 2. Okay. So this is 2, 3, 6. 6 times 4 is 24, over 3 is 8. Any question? So I'm just going to write down question B here, right? Because I guess you want to see the densities a little bit. So B, find the marginals density of x and y. And when you do this, right, just kind of think about, do x and y have the same marginals? Why or why not? So, right, we don't expect x and y to have the same marginals here because they don't seem symmetric, right? They don't look symmetric. The row of x and y doesn't seem to be the same. Don't seem to be the same. So doesn't seem to be the same. So right, they should not have the same marginals. But I mean, of course, we have to do a calculation to make sure. So for example, let's say what's the marginal of x? The marginal of x is to integrate this guy out with respect to y, right? So we have to integrate this guy out with respect to y. So 1/8, right? Question: y goes from where to where? What's the limit of y? So let me draw this region again, right? Y goes from where to where? So this is the region that says minus y less than x less than y. Y goes from where to where? Well, answer. There are two cases here. If x is negative, then you go from minus y to infinity. Sorry, if x is negative, you go from minus x to infinity. And if x is positive, you go from x to infinity. Do we understand? So this density of x is actually a piecewise function. It doesn't have a single function for every value of x. So I will skip the integration for now. All right. I won't do the integration. The reason is because it will involve some sort of integration by parts, and I think it's just boring, right? For you to see that me doing the integration by parts out. But that's the integral, right? Just to point out. So let's write down the density of y, which is the integral, right, of this. But integrate out the x. So x goes from where to where? This should be easier, right? Here x goes from
Negative y to y.
yeah, minus 1 to y, right? Yeah. And of course, this one is easier, more easily done because, right, the integral is easier. I think it's that thing that we calculate out, right? 4/3 y cubed e to minus y. Like that, right? Sorry, there's 1/8, right? So 1/6. All right. Any question? So C, they ask for find expectation of x. What should it be? Well, what's the integral? It's the integral of x, right, times the density dx, right? Going from where to where? Going from minus y to y, right? Sorry, for yeah, correct, right? From minus y to y. So for a fixed value of y. So what should this be? Yeah, it's just 0. How do we recognize that? It's both of them, right? Both of the integrals are odd functions of x over a symmetric interval. So no need to do the calculation, right? It's 0. Any question? So again, right, a lot of Calc 3 business, and you haven't seen any switching of the integral yet, right? Switching of the limits, but all right. So maybe one more question, right? Just to make sure we see everything. So let's quiz 7. This is question number 6.9. So they give you a joint PDF. Six over 7, like that. Okay. And A, they ask you to verify that this is a PDF, a joint PDF. So where's the support? The support here, right, is a rectangle, right? Yes, I draw it not to scale, but that's a rectangle. So basically, if you do this integral, you should somehow, right, figure out that this one. All right, but it's a pretty straightforward integral, right? So let's just skip that. B, compute the density of x. So what calculation is that? So you integrate out to y, right? Y goes from where to where? For a fixed value of x, y goes from
0
0
to
to
2.
2. Yeah. Right, nothing there. So rectangle is pretty easy in terms of region. Well, I guess it depends. C, probably x bigger than y. What would this be? Be a double integral, right? So any preference? Dx dy, dy dx? Probably not here, right? So this is a line x equals to y. Maybe. So x bigger than y is where? This region. Any preference? Dx, dy, dx.
You dx dy should be easier, right?
Yeah, easier in the sense that you don't have to split the integral into two different
Mhm.
integrals, right? Yeah, because right, if you do dx dy, x will always go from y to 1, and y would always go from 0 to 2, right? But if you do dy dx, and again, it's kind of funny because I think, right, the default most dx dy. But if you want to do dy dx, then y, right, depends on where x is. Y would go from 0 to x if x is right below these values, and y would go from 0 to 2 if x is above that value, right? So if you do dy dx, you have to do two integrals rather than one. And that's where, right, the choice matters. But here, funny enough, the default choice is the better one. So I guess there's no confusion. D, find probability of y bigger than 1/2. Condition x less than 1/2. Well, so first of all, there's no secret here, right? Just follow the definition. Right. And then we will write down the integral. So the top will be integral of what? The integral of the density and now, of course, luckily the region is a rectangle, so we don't have to worry much, right? X will go from 0 to 1/2, and y would go from 1/2 to 2. For the denominator, x would go from 0 to 1, and y would go from 1/2 to 2. Any question? So I want to finish 6.1 with, maybe finish or not. There are two more things I want to do with 6.1. The first thing is about the multinomial distribution, which I think I mentioned before, right? But it's actually within the context of joint distribution. So first of all, what does it do? It basically, right, is x1, x2, etc. up to xr. We're supposed to track the number of trials that result in, so x sub k, x sub I is supposed to track the number of trials that result in category I for I from 1 to R. So basically you have n independent trials each trial, right, has r possible results. Right, r types of results. And each type has probability pi. Okay. Again, the easiest one, of course, is the binomial distribution, where you only have two types of result, success or failure. But if you want to cast the binomial in terms of the multinomial, then you have x1 being the number of success and x2 being the number of failures. You track both. But you see, right, in fact, in these ones, one of them is redundant, because we always know that the sum of these random variables is n, right? Which is a number of trials, right? Because basically, each of them track the number of trials that result in category I. So if you sum them up, that's the total number of trials. So basically, if you know r minus one of them, then you know the last one. But, you know, or if you want to be like a little bit more specific, for example, instead of the binomial, you can think of the toss of a dice, right? Then let's say you toss a dice 10 times. Then within that 10 times, you want to track the number of ones, the number of twos, up to the number of sixes, right? That's the multinomial. And it's really a joint distribution, right? So the probability, let's say x1 equals to x1, x2 equals to x2, xr equals to x of r will be n choose x1, x2, x of r, p1 to the x1, p2 to x2, pr to xr, where of course the sum of these x1, x2, etc. up to xr must be n. Okay, any question? So that's the first thing I want to tell you. The second thing is along the line of the function, right, of two random variables, right? So we talked about function of a random variable, right, and how to find the density of it. But now we talk about function of two or more random variables and how to find the density of it. What's an example? For example, you have the joint density of x and y is e to the minus x plus y. You want to find the density of x over y. Okay. So what do we do? Well, first let's give it a name. Let's call it u. It's clearly a continuous random variable, right? Because x and y are continuous. So let's start with the CDF of u. Okay, actually, first of all, let's start with what? Let's start with the support of u. U should take values from where to where? You should take value from 0 to infinity. Because xy takes value from 0 to infinity, right? And then this will be probability of x over y less than equal to u. Notice it's very much the same thematic move that we did before, right? Start with the CDF, replace with a definition, and then just do whatever manipulation you need to do. here, notice that y is positive. So we can move y on the other side without changing the direction of the inequality. Or actually, you can just keep it the same. Basically, from this point, right? Then you would do the double integral over this region or this region, well, whatever that is. But so let's try that down. If I do dx dy, let's say, then right here x would go from 0 to u times y. Y would go from 0 to infinity. Right? And I just have to carry it out. So this will be the integral from 0 to infinity, right? E to minus y factor out because it's x. It's e to minus x, right? Uy. So that's going to be e to minus y times 1 minus e to minus uy. Right. That's integrating e to minus x. And then e to minus y, of course, integrate to 1, right? And then you got e to minus 1 plus u times y, right? And here we again recognize, so you just integrate, right? It's literally will be 1 over 1 plus u. So that's going to be u over 1 plus u. Sorry. So that's the CDF, right? Notice, right, the CDF here, when u go to 0 is 0. When u goes to infinity is 1. So that's true, right? Now the PDF would be differentiating this. This actually is easier to differentiate this one, right? So this minus log of differentiate 1 1 plus u gives you 1 1 plus u squared. Like that. Any question? All right. So I think, right, this is a good place to stop today, which is also the cap for midterm 2, right? Which is next Friday. So midterm 2 is not cumulative, but somehow it's probability is still around, right? Conditional probability is still around, that kind of thing. So, you're still responsible for whatever we discussed, right? Before midterm 1. But what I'm trying to say is the questions, right, will be focused on the materials we covered since midterm 1. So focus will be what? Midterm 1 is 1, 2, 3, right? So on chapter 5, right? And then 6.1. Okay. The setup is exactly the same as midterm 1 in terms of, responders, etc., etc. I will post a equipment check assignment soon to be due by the end of next Thursday. Okay. All right. I will see you next Monday.
Professor, could you scroll
Thank
up
you.
to the multinomial distribution?
Yeah. Any question there?
Yeah, I just missed the last one. Thank you very much.
Okay, sure.
Appreciate it.